Log on, tune in, find out. Another good idea from Cambridge.
On primitive ideal theory. Thank you.
Thank you. I'm sure you have all learnt from the posters on the streets that this year is the 800th anniversary of Cambridge University. However, what they do not tell you is the circumstances of its birth. So allow me to start by sketching a few details. In 1209, at a town 90 miles to the west, scholars and masters were fleeing an angry mob who had already hung several of them, apparently with the king's approval. Some scholars landed up in Paris. Others found their way to the River Cam. Various reasons had been given for the townsmen's outburst. Some say it was a common occurrence. Others blame the Pope for having excommunicated King John. One witness recorded that a woman had met an unfortunate end at the hands of a scholar. In view of the latter event, I would conjecture that the disturbances were caused by cunning scholars bedding their landlords' wives. Ample evidence for this practice is recorded by the Miller's Tale. Now let me just start off with a few lines from this tale, which I think also illustrates some points of view that non-mathematicians have of our work. Some time ago there was a rich old codger who lived in Oxford and took a lodger. The fellow was a carpenter by trade, his lodger a poor student who had made some studies in the arts, but all his fancy turned to astrology and geomancy. And he could deal with certain propositions and make a forecast under some conditions about the likelihood of draught or showers for those who asked at favorable hours. Okay. Well, in my feeling, many successful mathematical theories are successful because they are able to extract the finite from the infinite. So let me give an illustration of this with Goldie's theorem. Goldie's theorem, which I'm not going to state, but just its consequence, allows you to take a module for the enveloping algebra of a finite dimensional Lie algebra, which could be an infinite dimensional module, and to extract from it an integer, which is by definition finite and even strictly positive. And this provides a very powerful invariant of not only the isomorphism class of M, but also of the annihilator of M. And it turned out that it was possible, by using this invariant and the central character, to separate primitive ideals. And I would like to review the theory and discuss some of the problems that remain. I will only be talking about the case where G is semi-simple. Okay, well, to get some idea of what this number might be, let me give me two examples. So the first case, as you might expect, if dim M is finite, then simply, and of course I'm assuming a field of, let's just say the complex numbers, then the number n of M is simply the dimension of n. So that's the first one. And the second one is the following. Supposing M is an induced module from a Lie subalgebra of a finite dimensional module, then n of M is less than the dimension of n. and under favorable circumstances, equality holds. Okay, this first result already gives us some clues as to how to proceed for the general solution. In fact, if we write down M as being a simple highest weight module of highest weight lambda, and therefore lambda is in the set of dominant weights, then we know after the Weil dimension formula that we have the following. The product of all the positive roots of alpha lambda plus rho, where rho is the usual thing, half sum of positive roots, over alpha rho. We interpret this in formula by saying, so that's the formula, but how do we interpret it? We interpret it by saying that the following product, which of course is a polynomial, in fact even a monomial, but a polynomial of degree the number of positive roots, determines the Goldie rank, if you like. I didn't call it the Goldie rank before, but I'll call it the Goldie rank now, which is just simply the dimension of V, by evaluation at lambda plus rho, and dividing by a suitable scalar, which is exactly the one that makes this number, which has to be integer everywhere, positive integer everywhere, 1 somewhere. So that's that determines this function, the scale factor in the function. And furthermore, another aspect, so this determines the dimension. And secondly, this polynomial has a nice property that it generates a one-dimensional W module. Now, in order to formulate a general solution which will describe these numbers for arbitrary annihilators, we should find a way of describing the annihilators of simple modules. Annihilators of simple modules, as has already been said, are called primitive ideals, and the set of such annihilators is called the primitive spectrum. Well, just as here, we can now consider V of lambda to be an arbitrary simple highest weight module, and consider the map, well, of course, this is really a map from lambda to the annihilator of V of lambda. And in order to not have this annoying row here, let's just use the convention that this has highest weight lambda minus rho. So just slip slightly the convention. And then we have a map from the dual to the primitive spectrum. And furthermore, by intersecting with the center, and identifying the spectrum of this with H star over W, we have a second map to H star over W, and as life is good, the composed map is just the quotient map. It already gives us a lot of information about the primitive spectrum, which and so primitive ideals are separated. They're separated by the images of this map, and that's sometimes called separation by central character. Now, fortunately, Duflo proved that this map is surjective, so we don't lose anything when we look at the image of this map. So we have our problem now of describing this number, this Goldie rank, as a function of lambda. Now, because of this map here, we can also say that two primitive ideals will be distinct if their images here are distinct. So if we want to know what the fibers of this map look like, we should describe when we only need to describe when the annihilator of V of lambda contains the annihilator of V of y of lambda. Now this will solve this, if we can solve it, will tell us about this mysterious number. And this, if we can solve it, will tell us not only about the fibers of the map, but the inclusion relations between primitive ideals. So we've actually given ourselves two problems for the price of one. And in fact, there's a third problem, which is the following. You take u of g over the annihilator of V of lambda. This has finite length as a bimodule after Dixmier, and one could ask, what are its composition factors? So we've actually got three problems. And my long-term goal or viewpoint was that problems, these three, but perhaps others as well, as we'll see, should all be solved in terms of some basic data. Solved in terms of some basic data. And what should this basic data be? Well, nowadays we all know what it is, but at that time I made the guess that the basic data should be the Verma module multiplicities. That is to say, the number of times a simple module occurs in a Verma module. That's what I took to be the basic data. A few years later, I considered analogous problems to these, but in a commutative context. And then the question was to use this. So far, I haven't told you how to go from the basic data to these questions, but however you do it, in the commutative context, you should use the same recipe. Now, we all know that when you quantize, when you go from the commutative to the non-commutative, things don't quite fit. It's like trying to fit a square peg into a round hole. And the beautiful fact is that the reason for this not quite fitting is that the data is different. That's something one should keep in mind. I would like to compare it to two cooks baking a chocolate cake. One uses Belgian chocolate, the other uses English chocolate. They use exactly the same recipe, but the results are quite different. So, what is our goal? In number one, goal one is to describe these this number, and let me now give the number a name. I'll call it the rank, the Goldie rank. That's just another name. I haven't defined it. It's not really necessary in this lecture of this. And let me, for simplicity, restrict to dominant integral weights. So I write that as lambda plus, and because of this row shift, I'll add another plus. That's just rho plus p plus. And then, since we don't know what this is, we'll give it a name, which is p of w lambda. Well, that's the function that we want to determine.
Is it a domain?
No, of course not. That's the fun. This is a number. It would be 1 if it was a domain.
Sorry, I mean not domain. I mean it's
A prime ring.
yeah. It has no nilpotent ideals. Yes.
No. So that's what we want to compute. And let's convert, instead of talking about these numbers, let's make the following identification. Identify W with the class of M of W lambda in the growth of D. And let's identify, let that identification give V of W lambda the element in the group ring of the Weil group, which I'll denote by A of W. So that's just a way of encoding these numbers. And then one of the theorems I proved was the following, that P of W is equal to, now here I'll put some star which designates a scalar, of A of W to the minus 1 rho to the M, where M is the least positive integer, least non-negative integer, perhaps I should say, which makes that expression on the right non-zero. Now, perhaps one should remember that this has positive and negative coefficients in it, so the M could be bigger than 1. Now, what about this scalar? This is still a very much open problem. And this, in fact, if I'm going to list some problems, this is one of the first. The natural conjecture is that the scalar is, of course, partly fixed by requiring these to be positive integers in this domain, since they represent these numbers, but somewhere taking the value 1. So, if you like, conjecture, there exists lambda 0 in P, not necessarily dominant, such that P of W lambda 0 equals 1. And in fact, lambda 0, if it's dominant, would correspond to Goldie rank 1. If it's not dominant, then it's totally mysterious. And another part of this problem is to interpret what does it mean for this to have a value 1. Actually, this theorem has much more to it. And let me just say it in a few words. These polynomials are really identifying families of ideals which have different central character. Then these polynomials corresponding to each family turn out to be linearly independent. So the P of W are linearly independent unless they're equal. And one can divide them into families so that they form a basis of a representation of W. So we can divide them into families. I'll just write some notation. It doesn't mean so much. We have what's called a double or two-sided cell. And then these guys form a basis for a W module, for a simple W module. And moreover, could raise this a little bit. Moreover, the ideals corresponding to these guys, because you see each one comes with some ideal, all have the same zero variety. So, or associated variety, should I say, so that the variety of annihilator of V of y of lambda it doesn't depend on lambda, by the way, and it doesn't depend on y in this subset of the Weil group. And furthermore, this gives a simple module S, say, and the simple module is exactly the one that Springer attaches to something to which he also attaches here. This turns out to be the closure of some nilpotent orbit. Let me just write it like this. And the relation between S and O is Springer's correspondence, or just O. Now, this gives you the possibility of starting from a nilpotent orbit and finding a primitive ideal whose associated variety is at orbit. All you have to do is to look at your basic data, compute these polynomials, and compare the representations you get to the representations given by the Springer correspondence. And this program was carried out by Barbash and Vogel. I'm not quite sure if they totally completed it. And they were able to show that, maybe with a few holes, I don't remember, that every nilpotent orbit could be associated, or was the associated variety of a primitive ideal. This gave, these ideas gave Kazhdan and Lustig the clue for what these numbers should be. And then Lustig, actually quite recently, found a case-by-case free way of proving the statement I made before, that all nilpotent orbits occur. So that was quite satisfactory. Now let me go to problem 2. Again, we will make use of these objects, which you can now recognize as Lustig bases. Kazhdan-Lustig bases, or one of the many bases they wrote down. Well, before they were doing these clever things with Hecker algebras, I had considered the following object. Of course, that's very easy and natural to consider. It's just the left ideal generated by this element A of W. But then it turned out that that wasn't quite the right thing to consider, but rather this object, which is the Q-linear span of all the guys which occur in here. So when we write out W of A W in terms of the AY basis, then we will get certain coefficients. We take all the coefficients which are non-zero, we call that the support, and then we take the linear span of all that. By an accident, this is a left ideal. So it's very nice that you associate a left ideal of W to a primitive ideal of U of G. Left ideal in Q of W. Of course, we didn't put those brackets around to be completely obvious. With the brackets, you need to use some positivity property. And then I prove the following statement. Well, this makes sense, but by definition of that, that means it's just in the support. And Vogel proved the opposite relation by return mail. This, I might say, was before email. He didn't spend very much time proving it. So we now have that very nice result. And now we can say that this nasty problem is completely solved by using Cauchy-Lustig polynomials. Now, let me go to problem number 3. So we've done with problem 2. Let's go to problem number 3. And after Duflo, U of G over the annihilator of V of W lambda has a simple circle. This is just because this is a prime ideal in a Noetherian ring. It has a simple circle as a bimodule. And he showed that this simple circle is naturally given by an involution in the Weil group. And we call the involutions that occur Duflo involutions. And what I found was that one can use the Cauchy-Lustig polynomials to determine this involution. It's interesting to note that previously, at this step, for example, we only used the Cauchy-Lustig polynomials at Q is 1. Here we need the full polynomials, and there's a very simple recipe. Lustig then found that these elements, these Duflo involutions, provided identities in what he called the J ring. So he introduced a J ring. Well, first of all, these guys live in a group algebra, and they actually should be thought of as living in the Hecker algebra. The Hecker algebra has a multiplication. That multiplication is rather complicated. He then found a truncation of that multiplication, which was still associative, in which life became much simpler, and he called it the J ring. And he computed the structure constants of that J ring very nicely in terms of data involving the component group of the nilpotent orbit. And then I showed that the structure coefficients, its structure coefficients, determine, this is sort of very natural, the circle of the maps, which I call the K-finite maps, so the finite for the local action, of one simple highest weight model into another. So this is just Hom cut down by the locally finite elements. Another rather tricky fact, which used some properties of the Cauchy-Lustig setup, was that this circle was nearly all the module. In other words, when you divided by the circle, you got something of lower Gelfand-Kirillov dimension. This is also true here, by the way, but it was true more generally. And so this actually determines the fractions. It's possible to go to the fractions of this. So what we learn is, although we haven't really solved anything about problem 3, we at least know that the fractions of this is determined by these coefficients in the J ring. And then with Stafford, so then contribution from Toby Stafford.
What do you mean by fractions?
Well, you can localize. So in this Goldie, I don't know if this is a very good terminology, But in this Goldie machinery, you can localize and get down to, don't really want to explain it now, but you can think of this as a module over the ring of fractions of u of g over the annihilator of v of w lambda.
And by circle you mean quotient or submodule?
Submodule. So with Stafford, we showed that this also determines the full guy in the following sense. This guy is canonically determined by this guy because it's the largest submodule which is finitely generated on either side. So that determines this. So then you might believe, why not, that Kazhdan-Lustig polynomials should determine this. So question, this is lots of problems here. Do KL polynomials determine this as a bimodule? And just let me remind you that that bimodule is finite length. Now, if you take the special case where W is Y, it sometimes happens that this is very much bigger than this guy, and sometimes it has the same ring of fractions. Turns out that it's a little better because it can have the same ring of fractions and not be the same. And this was done by, I just say it very quickly, this was done by Mazur, Chook, and Stroppel. So in some sense, what they told you is that this is definitely a bad ring because it isn't the maximal finitely generated submodule in its ring of quotients. So that sort of suggests that we should change problem 3 to the problem of determining this. Still, I don't know what the answer is. Let me give you a sort of taste of probably what is the wrong answer, but just a sort of flavor of how I think things should go. So let me just put down the wrong answer, which is actually quite frequently correct, but let me just write it down anyway. So this is correct for certain induced ideals. Namely, we know that Q of W of A W is a left ideal, and therefore it can be written in the form like this, where E of W is a nilpotent element and self-dual in some obvious sense. That determines E of W uniquely up to a scalar. The scalar is then fixed by demanding that the coefficient of the Duflo involution occurs exactly 1, exactly with coefficient 1. And then the idea is that the remaining coefficients determine the multiplicities of what remains. Now, this answer is wrong except in one family of cases, but I put it down just to illustrate the sort of philosophy one should have, a very simple-minded philosophy, I might say. Now, let me get back to the English chocolate. So we've done all this in the context of enveloping algebras. What about the commutative case? And when I looked over the shoulders of Barbash and Vaughan, I realized that you could define polynomials analogous to the Goldie rank polynomials, which turn out to be almost the same as them, by analyzing growth rates in orbital variety. So let me take a nilpotent orbit and intersect it with n plus. And then after Spaltenstein, this is a equidimensional variety, and any component has the same dimension, exactly half the dimension, in fact, of the original orbit. And is also Lagrangian. So it's a very nice object, and one calls it an orbital variety. Actually, it's the only term I've invented in mathematics, and I invented it because I was on the London orbital. So that's the origin of the term. So, of course, the orbital variety should be thought of as sitting in n plus, and therefore its ring of fractions, I mean the ring of functions on the closure, is an ideal inside S of n minus. So this is an ideal in S of n minus, and I regard it as the commutative analog of a primitive ideal. Right? So a question, so there's another problem. This, of course, is stable under the torus and it has a character. Determine the character of this. Determine this. Now, that's not an easy problem. The corresponding problem for simple highest weight modules was solved by Kazhdan and Lustig, or at least they suggested the solution, and it was only solved by using something very weird. Well, at least I regard it as weird, but now young people find it just breakfast material. So this is going to be difficult. However, what is a little easier is to describe the asymptotics. The asymptotics are given as polynomials on H star and are almost the same as the Goldie rank polynomials. Moreover, these polynomials generate exactly Springer's representation associated to the orbit and the trivial representation of the component group. So,
you mean the dimension of support, yes?
what I mean is you look at the dimensions of the weight spaces and then you just look at the way that behaves. So this measures the behavior of the dimension of the weight spaces.
So what is a polynomial? The leading coefficient, or?
Well, you take a sum of the form dimension of V of this with respect to some weight lambda. This is an element of H star, so you evaluate it. Let's not be too precise about this. You evaluate it on some dominant weight, and then you take the dimension of this where lambda of c, I'm sorry, put it like this, is less than some integer. Right? Then you get a polynomial which has a leading coefficient. So this has a leading coefficient. And the statement is that the leading coefficient as a function of xi is a polynomial divided by the product of the positive roots. And that's the polynomial. Okay? So it measures the asymptotics. And so what should this polynomial be? And of course I conjectured that it was exactly the same as this. It was given by the same recipe, but not by using these fundamentals, not by using Belgian chocolate, but by using English chocolate. And the Rostman proved this. So this is governed in the same way by new fundamental data. Moreover, relatively recently with Hinich, I settled problem 2 for the inclusion relations between the orbital varieties. So I said orbital varieties are like primitive ideals. You can formulate a similar problem to problem 2, and then you can ask whether any two are included. And the answer is exactly as before, except that you use the new data. So you may therefore ask, what is this new data? So this new data is, of course, now well known and well understood what it is about. And this data is, just as the case of the Weizmann modules, is the new data is just is given by the matrix relating two natural bases of the zero Borel-Moore homology of the Steinberg variety. One basis is, of course, given by the irreducible components. The other basis is got by the action of the Weil group on this homology, in some sense exactly analogous to the Weizmann module. Think of the Weizmann module as being generated from 1 by the elements of the group. So M of W lambda is W applied to 1. So if you have an action of the Weil group on the... Sorry? Steinberg. The Steinberg variety. The Steinberg variety should be thought of as the fiber product of the cotangent bundle of G over B. This is the best way to think of it. With respect to, I think I learned from Hinich, you should put this at the bottom, pi, that's not, pi of G over B, where pi is the moment now. So this presentation of the Steinberg variety allows you to do this business of correspondences. And of course, this has been thoroughly studied and written about by, for example, in the book of Chris and Ginsberg. The only trouble is that they don't tell you what the matrix is.
What's the second basis? First one is basis of components.
The basis of components, and the second one, you take the diagonal component, which you think of as the Weizmann module of highest weight lambda, and then you use the action of the Weil group on the homology to give you the other components. So if you like, the Steinberg variety has S of W as components, and it has W S of 1 as other guys. All right, and so this matrix is just the coefficients which relate these guys. It's that. So, as I say, you can read all about this in Ginsberg and Chris and Ginsberg. The only problem is that he doesn't tell you what this matrix is. It's a bit of a scandal that we have this open problem in mathematics, which would determine so much, because it gives the inclusion relations between the orbital varieties, and therefore it gives the inclusion relations as a special case between the nilpotent orbits. So problem, what are the matrix coefficients? So, well, I don't want to bore you too much with lots of problems, but let me just say a few words about what the problems I've written down already. Almost nothing is known about this. Even if you know these numbers over here, that only gives you the asymptotics. Almost nothing is known about this. And in fact, the only thing is known, that I know of anyway, is the case of the minimal orbit. The minimal orbit has associated to it, in other words, if I put the minimal orbit here, has associated to it several irreducible components, orbital varieties, and I was able to compute this character in all cases except E6, F4, E7, and E8. A student who had just got married and was spending her summer in the Weizmann did the one remaining case in E6, but then she simultaneously divorced her husband and abandoned me. Two totally unrelated events. And so no more progress was made on this problem. Another way to go is to consider the differential operators on an orbital variety. This was another one of those very attractive developments which didn't come to very much. So we have this orbital variety, or maybe its closure, and we consider the ring of differential operators on this. And hopefully, this is this of course is a prime ring, primitive, this is a domain, and hopefully it would somehow contain a quotient of the enveloping algebra. In other words, we should have a map of U of G to here. And with the kernel being a completely prime primitive ideal, so this is hopefully, where, so we have now an injection, and again, hopefully, the variety of I should be the orbit which contains V of W, V of G of V. Now, in fact, this theory works wonderfully well in what one might call the commutative case. So, works well if V is sitting inside the nil radical of a parabolic with M commutative. And this is also the case. This is partly because the orbital varieties are orbits for a Levy factor, for the Levy factor of the parabolic. So that's a nice case, but unfortunately the other cases don't seem to work as well. So maybe I should end with the most basic problem in this whole business. So what's the most basic problem? I'm sorry I don't have any much to say about it. And that is determine or at least enough completely prime primitive ideals. That means i.e. that U of G over Q is a domain. And this would seem to be not that difficult, but it turns out to be really rather nasty. And in some sense, this whole program is similar, to my mind anyway, to the situation for unitary representations. One had already from Langland's a classification of all Banach representations, but one didn't know which ones were unitarizable or which ones admitted a positive definite Hermitian form. And here we have a complete description of Goldie ranks, so that we know all about the primitive ideals and their ranks, but we don't know the ones of rank 1. And so it's sort of analogous, and one might push this analogous further and ask whether it had anything to do with unitarity. And a vague dream that I had was that not only there would be Goldie rank polynomials which would determine unitarity, which would determine complete primeness, but there would also be sort of unitarity polynomials which would sort out the mess of the unitarity theory. In any case, this sort of led me to the idea that unitarity should be used, and I asked Weizmann about it, and he said, oh, that's all nonsense. And then he went away and proved the following nice result. So, view this as a representation, as a Harris-Chandra module, let's put it like that, as a Harris-Chandra module. If it admits a positive definite Hermitian form, with respect, of course, to the appropriate choice of real form, which makes the diagonal action the compact subalgebra, then, of course, Q is maximal. That's trivial. But then Q is completely prime. And Weizmann and Barbash have used this rather successfully. Another idea which I can tell you about because it doesn't work is something which I thought was very attractive but just doesn't seem to go anywhere, but maybe somebody here will understand what to do. And that is the following. One would like to create a completely primitive ideal from Dynkin data. So you start with a Dynkin data and you write down a completely primitive ideal. So let's take this to be the Dynkin gradation associated to a SL2 triple. And let's call N2 everything with I bigger than 2, and N1 everything bigger than I bigger than 1. Then it's a rather easy fact which uses the fact that the parabolic, which I didn't write down, but it's a usual Dynkin parabolic, acting on E gives a dense orbit in N2. So that leads to the following fact. If we look at S of G and we map it to S of N2 by restriction of functions, and then take the N1 invariance on both sides, then the kernel of this map is just the ideal of definition of the orbit closure. Well, this maybe one should write it as G of E. So all you have to do is find the enveloping algebra analog of that, and you've got your quantization. Now, in fact, probably with greater wisdom, we know that there's a better path. The trouble is that this tries to push you to think of the parabolic as the negative parabolic plus half of G1. And that in general doesn't give you a subalgebra. So a better way to do this is to take, well, I have it written down somewhere, what I should just call, and I'll just write it down quickly, to pick N1.5, which you can guess what it is, and this is of course just the quantization of the Sloterdijk slice. Whether or not this works is another matter, but it's a cousin of this one, and it's sort of a bit better because at least this guy, which you can all interpret, is at least a subalgebra. So that's another possibility. And of course one would somehow think that despite the fact that it's a rather nasty algebra that you get in the end, one would rather like to think that this procedure would work.
Yeah. Yeah, I just wanted to ask if this condition is related to graded of Q being a radical ideal.
Which condition?
the condition that it's completely prime?
Well, unfortunately, it's sort of a little more complicated. So it can be that, and rather frequently is, it can be that U of G over is a domain, but the graded of is not prime. Of course, the other way around, it's trivial. If it is prime, if this is prime, then this is a domain. But it can unfortunately happen that
It can be non-prime, but can it be a non-radical?
well, the radical is the prime ideal. So somehow, no, it can't be, because one knows that these the variety of this is irreducible. So.
So it's an irreducible variety, but not prime. So that means it is not
Exactly, and that's a really nasty thing. I might say another problem was to try to associate to each, well, another problem, a problem I already mentioned, was to associate to each nilpotent orbit a completely prime primitive ideal. And so Vogel had the attitude that there's only one which has this property. And if there is another one, it just doesn't have that property. But this didn't really go anywhere. It didn't manage to. Okay, I'll stop there. And, well, I read you the first part of the Miller's Tale, and you can think of my lecture as being the middle part. And so I would like to end up with the last part. And at this point, if you know the Miller's Tale, you would understand it's advisable to switch off the microphone.